Hi there. Today we're going to be talking about quantum tunneling. And in quantum tunneling, what we see is strange things happening due to the effects of, the quantum nature of the world. Look at this diagram to one side here, and we can see the classical picture is an electron comes along and it is repelled by an electric field, was repelled by something being in the way. And that's all well and good. It turns around and goes back. Now, in the quantum picture, we recognize that our electron has a wave-like properties. So that wave-like properties means that there's a probability that the electron could be in a number of places, and there's a finite probability that the electron is going to be able to tunnel its way through. So actually be located outside, beyond the barrier, and therefore it allows the electron to move through the barrier. And this is the process known as quantum tunneling. And we can see it in a number of varieties. It's actually a really, really useful task. So that's what I'm going to do today, is I'm going to talk about how this happens and some examples of this, and give you a practical problem which you can solve as well. So alpha radiation is a really good example of that. In the non-quantum world, the classical world, the alpha particle would be locked inside the nucleus because of the strong forces, and it wouldn't be able to escape. And that, in that case, it's the potential energy caused by the strong and weak forces was mean it would never be able to escape. And at the same time, an alpha particle could never enter because there's a barrier of potential which would cause it to repel away. And it'll only be able to enter if it had enough kinetic energy to overcome that barrier. Whilst if we look at it as a wave function, well, as a wave function, what we can see is here, my alpha particle has a potential to be occurring beyond that potential barrier. And that is why we see alpha radiation being able to escape the nucleus, because of the quantum nature. And if we consider it as a quantum waveform, it means there has the opportunity to potentially escape. And actually, if we look at the numbers here, it's really quite interesting, because it appears that the half-life of a particle is really tightly tied into this likelihood of escaping. So this is where we see something which is probabilistic, and we're quite aware of, which is half-lives, actually being driven by the probabilistic nature of quantum theory, which is a really interesting tying together. Now, the likelihood of something escaping. Okay, so this likelihood is going to be down to three things. The thickness of the barrier. If it's an actual barrier, then the bigger the barrier is, the less the chance of something escaping. The amount of energy required. So sometimes we don't have a physical barrier, but we might have a potential barrier, as we spoke about in the example of the alpha radiation. And also the mass of the object. The more massive an object, the less likely it is, due to its wave function structure, of being able to escape anything. And that quantum tunneling, and I quite like the idea here, is if you look at the diagram, the idea is that quantum tunneling is it just because of quantum effects, it means it tunnels through any barrier. It breaks down any barrier. And the bigger the barrier, there's an exponential decrease of whether the wave function is going to be able to exist on the other side. And that's we're seeing it decaying down, and so therefore it gets to nothing, there's no chance of it escaping. Let's consider a question which is related to this. So here we're going to think about an electron. An electron is on one side of a barrier of thickness 4.7 times 10 to the minus 9 meters. If the electron is found on the other side of the barrier, what is the minimum uncertainty in its barrier, in its momentum? So that means that we've got to recognize that the uncertainty of the location of the electron is got to be at least equal to the thickness of the barrier. So think about which formula you're going to apply to this. And here we would use uncertainty principle. We know the relationship between the location and the momentum is greater than the values of h over 4 pi. And so the uncertainty position is the thickness of the barrier, which is the number we can plug in. And that means that our only remaining unknown is the uncertainty of the momentum, which comes out as 1.12 times 10 to the minus 26 kilograms meters per second. Now, why is this useful? Well, the actual process is really useful because it means that we can start to find situations where we can have barriers that electrons can tunnel through. And if they can tunnel through, it means we can have things like 3D touchscreen displays are based on these ideas, STM microscopes, and flash memory are all actually based on quantum tunneling effects. So it becomes really useful in the real world as well. And that is my quick overview of quantum tunneling.